Hello everyone, my name is Nico. I'm an assistant professor at UNC Chapel Hill. And in this lecture, my goal is to bring you from the very fundamental principles of wave propagation all the way to an active research area called computer generated holography. We have reduced the amount of equations down to the very minimum, but we hope to convince you that great technology can be created when optical engineering meets computer sciences. We will present a series of tools to simulate the propagation of optical waves in free space and in basic optical systems. And then we will assemble those tools into algorithms to solve inverse problems in optics and to compute holograms. The slides for this lecture are available on our website along with the MATLAB code for the simulations that we will show. And we encourage you to run those simulations on your computer and to modify the simulation parameters to familiarize yourself with those tools. For the purpose of this lecture, we will assume that light is a wave. That is, a perturbation of the electromagnetic field in space and time that satisfies the wave propagation equation. So to give ourselves an intuition of what this looks like, we can consider, for instance, a point source at the red dot. And we'll assume that at this location, the electromagnetic field oscillates in a sinusoidal form. And if we look at it in space and time, it will look a little bit like this. A wave propagates away from the source. We can characterize the wave at the red dot by defining its amplitude A and its angular frequency omega. Sometimes you will find alternate definitions, the wave period or the wave frequency. All these definitions are equivalent to each other. In optics, we don't really like to work with cosines and sines, so we instead refer to the wave using a complex wave function, and the oscillation will be the real part of A exponential minus I omega t. And very often we won't write the real part in our equations, and we simply write A exponential of minus I omega t. Once we are in steady state, we may be interested in characterizing the wave at another location in space, for instance, at a certain distance r from the source. As you can see, it takes a certain time for the wave to travel all the way from the source to the secondary location, but we can quantify this delay in the form of a phase delay, e to the I k r, where r is the distance that is needed to travel, and k is the wave number or the spatial angular frequency of the wave, which is related to its wavelength. Because the wave propagation equation is a linear differential equation, the sum of any two solutions is also a solution. So for instance, in this example, we consider the superposition of 2 point sources, and we can calculate the oscillation at any location in space simply by repeating twice what we just did in the previous slide. The first point source oscillates with amplitude A and angular frequency omega, and the oscillations that it creates somewhere else, for instance in B, is subject to the phase delay kr. Then we add the contribution of the second source, which is another oscillation with amplitude A, synchronized and in phase with the first one at angular frequency omega. For the second source, light travels a distance r prime to get to B, which introduces a different phase delay. We add the two complex waves, and if we simplify the equation a little bit, we find that the amplitude of the resulting wave only depends on the difference dr between r and r prime. If dr is a full number of wavelengths, the waves add up. We call this constructive interference, and there is plenty of light. But when the difference of propagation path between the two waves lands at half a wavelength, the two oscillations cancel each other out, and there is no light. We call this destructive interference. The generalization of this method to a large number of point sources is called the Huygens-Fresnel principle. The idea is that we can simulate the propagation of any wave through free space simply by decomposing it into a superposition of many point sources. For instance, in an optical system, we can consider a contour in the far field where there is no light, and we define our wave by its phase and amplitude when it enters this contour through a finite size window. To calculate the field anywhere within the volume, we decompose the border into a uniform distribution of point sources, matching the phase and in amplitude of our wave at any point. We then add the respective contribution of each of these point sources to the field at the location of interest and sum their contributions. For optical beams that propagate mostly along an optical axis z, the propagation of a wave decomposed into point sources can be written as an explicit convolution formula called the Fresnel wave propagation equation. If the phase and the intensity of the wave is specified anywhere in the 2D plane, for instance at z equals 0, then the wave can be calculated at any other location x, y, z in space, simply by adding the contribution of all the point sources with their respective phase delay. We have implemented a MATLAB function that allows you to perform this operation in a computationally efficient way by specifying the 2D complex field as a 2D grid of complex values, the wavelengths, the desired propagation depth z, and the sampling size of your domain psx, psy along each axis. Here's an example simulation. We consider the propagation of a wave given by a custom amplitude profile, for instance the UNC logo. We have 300 pixels along the y and x axis and a pixel size of 10 microns. In this example, we set the phase to 0 everywhere, for instance, and we propagate the resulting complex wave. So this is what the amplitude of the wave looks like, a centimeter away. You can see the effects of wave propagation, particularly along any sharp edge. We can redo the same simulation, but this time assuming that the phase is, for instance, randomized. That's something we could do experimentally by placing a diffuser into the beam. And if we look a centimeter away, we see a different amplitude profile that carries the effects of the diffuser in z equals 0. We invite you to download the code and run this simulation on your computer. You can modify the parameters like the pixel size, the wavelength, and the propagation distance and see how it affects the results you obtain. You can also modify this code, for instance, to show that the forward propagation of a phase conjugate wave yields the same image as the reverse propagation of that wave. In general, the Huygens-Fresnel principle allows us to simulate the propagation of light through pretty much any linear optical element, but those are not always computationally efficient. Besides free space, the second case where wave propagation is easy to calculate is the FF system. Here our incoming wave A is at a distance f from a lens, of focal length f, and we would like to compute the resulting complex wave at a distance f on the other side of a lens. In this particular configuration, we can calculate the complex wave at coordinate u along the b-axis by adding the contributions of individual point sources matching the state of the wave A on the x-axis. We see that the phase delay needed to take into account the contribution of individual point sources linearly increases with x and with f. The resulting equation for the complex field B along the u-axis is nothing else than the Fourier transform of the complex field A if it is sampled at k equals u over f. In short, we say that the FF system operates an optical Fourier transform of the complex field. We have also written a MATLAB function to simulate this operation. In field 1, we supply the complex field at a distance f from the lens. The 2D grid is matched to a specific pixel size psx, psy along each axis, and the model parameters f and lambda. The output of this function is a complex field, field 2, on the other side of the lens at a distance f. The number of elements in field 2 and field 1 is the same, but their physical spacing is different and matches a new sampling of the space with new pixel sizes, ps big X and ps big Y. Our second simulation utilizes this function to simulate the propagation of light through an aperture-limited optical system. So here's our input field. It's an image of Mr. Fourier, which we picked because it has high and low spatial frequency features. Using the simulation of an FF system, we can calculate the field in the Fourier domain. Well, this is what we find. What you see here is on a log scale. That is because there's a very bright dot in the center. And that is because our image is a natural image. So there's a lot of low spatial frequencies in it. To simulate an aperture-limited optical system, we restrict the field that is allowed to continue through the optical system using a pinhole aperture. So in the simulation, we set to 0 all the values of the complex field that are covered by the aperture, and then we continue by simulating the propagation through another FF system. And this is what our output looks like. Here what you can see is that the output field is a reversed image. Well, This is what we expect from a 4F system. What you can also see is that the high resolution features of the initial image have been cut off. The image is slightly blurry. And this illustrates the effects of the aperture, the resolution limit of our system. Much like in a microscope, the numerical aperture, the maximal spatial frequency that is allowed to go through the optical system, determines the size of the smallest feature that can be resolved. So you can run the simulation code yourself. But what we invite you to do is play with the parameters. If you change f or f prime, you'll change the size of the output. If you change the aperture size, you will change the resolution of the output image, the total amount of light that travels through. And overall, you will find that the simulation you get matches pretty much what is known to experimentalists when working with imaging systems. At this point, you now have all the tools you need to simulate the propagation of optical wave through the majority of optical systems. You can simulate each lens in the system with a dedicated FF lens operation, and you can adjust the mutual distances using the free space propagation operation. In this example, you can simulate the FF system associated with lens 1 first. Then you virtually propagate the field backwards by setting a negative propagation distance z. And finally, you simulate the wave propagation through the second FF system around lens 2. We provide an example application in which we use lens and free space propagation to simulate the propagation of an ideal point source through an optical microscope. We run the simulation at various depths around the image plane, and with that we can estimate the point spread function of the optical system, and we can see how simulation parameters affect its size and shape. In all our previous simulations, we rely on the fact that once the phase and the amplitude of a wave is known at a particular plane, the propagation is deterministic, and it becomes possible to calculate exactly the phase and the amplitude in the rest of the 3D volume. But there are many more advanced optical configurations where those conditions are not met. For instance, we may only have access to partial information. If you have a camera, it will record the intensity and give you access to the amplitude of a wave, but it will not give any direct information about phase. Sometimes the information is distributed, which means that we may have access to partial information at multiple locations, phase in one plane and intensity in another, for instance. All those situations are inverse problems that are more difficult to solve because they are nonlinear, non-convex, and with no explicit solutions. Sometimes there is a solution, sometimes there are many suitable solutions, and sometimes the problem is over-constrained and there may only be suitable approximations. In the next slide, we will show you how to solve such problems using iterative optimization algorithms. Let's start with an example. We consider an expanded laser beam. If the beam is clean, we know very well what the amplitude and phase of that beam looks like. Along the beam, we place a transparent object. For instance, it's a prepared microscope slide with a few layers of biomaterial on it, cheek cells, for instance. Since this is a transparent object, the amplitude is not really affected. But because the refractive index of our object and the thickness is varying in space, the phase is now perturbed. The object is perturbing the phase of our laser beam quite significantly, and we would like to calculate it. So at this plane, we now have partial information. We know the amplitude of the laser beam, but we no longer know what the phase is, and we'd like to calculate it by doing a measurement. If we were to put a camera right there at this plane, things would not really improve for us because, just as we said before, cameras do not collect phase information, just amplitude. So what we are going to do is let the wave propagate a bit, either through free space or through an optical system. We can do either because we have the tools to do that. And somewhere else along the optical path, we will place a camera and record the intensity and get the amplitude. So in that second plane, we also have partial information. We have the amplitude of the beam, but not the phase. And we have a convenient optical system and the tools to simulate how a wave propagates back and forth through them. To solve these types of incomplete problems, we use the Gershber-Saxton algorithm. We begin in the plane of the object. Here we know the amplitude, it is provided by the laser, but we do not know the phase. So in the initialization step, we're just going to fill in the gaps by assigning a random phase to our field. We know this is not the solution we want, but doing so allows us to use the propagation tools that we have. and we're going to find a way to make things better. So we begin our algorithm with the first guess of the complex field, and we use the tools we have to simulate the propagation from the plane of the object to the plane where the camera is in B. We calculate the phase and amplitude of this propagated field, and the amplitude we get may not match the data that we recorded in this plane with the camera. So to fix it the best we can, we keep the phase, but we update the amplitude of our complex field with the experimental data using, for instance, the square root of the intensity measured by the camera. We take this new and improved complex field and we simulate with the same tools the reverse propagation through the optical system, but backwards, which brings us back to the original object plane in A. Here, the complex field we have now has a new phase, and that phase is perhaps a better guess of the phase we're trying to measure. So we're going to keep it. However, because we have been changing things in the steps before, the amplitude of our field now is no longer going to match the amplitude of the laser beam. So here, we're going to do the same type of update and enforce that the amplitude of our field should match the amplitude of the laser beam. And we're now back to square one, but with a better guess of the complex field. The principle of the Gershberg-Saxton algorithm is that by repeating this operation many times, hopefully the algorithm converges and the amplitude updates stop being dramatic changes. If we stop the algorithm in A, then after n loops, we get an estimated value of the phase and our problem is solved. It is important to mention that the Gershberg-Saxton algorithm is known to converge, but there is no proof that it always does. Also, the solutions are known to be suboptimal. There are more advanced optimization algorithms that can do better. That being said, the algorithm is nonetheless popular because it is intuitive, it is easy to implement, and it is tied to a simulation model, so it can be easily tailored to custom optical systems. Computer-generated holography is a type of problem that is easy to solve using Gershberg-Saxton algorithms. The optical configuration is simple. A coherent light source illuminates a spatial light modulator. Each pixel of the SLM is a liquid crystal on which the computer can apply a custom voltage, which introduces a local phase shift. By specifying the voltage pixel by pixel, an SLM can therefore create a 2D phase modulation on demand. The modulated wave, either transmitted or reflected from the SLM, and propagates in an optical system. Typically, this is a Fourier lens in an FF system, as we've seen before. Light propagates towards the image plane, and the phase fluctuation induced by the SLM lead to a special reconfiguration of the intensity function. The goal of a CGH algorithm is, knowing what intensity we want in the image plane, to calculate what is the best phase modulation we need to apply in the SLM phase to obtain this illumination pattern. So we have implemented the Gershberg-Saxton algorithm for computer-generated holography, and at each step of the iteration process, we can simulate the propagation of light through the optical system and compare the rendering of the hologram to the distribution that we're trying to create. We compare those two elements using the accuracy, which is a measure of mismatch, and we can plot the accuracy as a function of the number of iteration or the computation time. And what you can see on this diagram here is that the more we wait, the better the rendering gets, up until a moment where the algorithm stabilizes to a certain level of accuracy. More advanced algorithms, like for instance direct optimization, are able to use advanced optimization techniques, so for instance gradient descent, in order to identify holograms that are actually better than what Gershberg-Saxton can create. Those algorithms are known to take a lot more time to compute holograms because they are very greedy in terms of computation. But as you can see on this diagram, they eventually find holograms that have an even better accuracy beyond the point where Gershberg-Saxton algorithms stabilize. So now we understand what are the great challenges of computer-generated holography. From this diagram, you can see that we want not only algorithms that improve the accuracy of the holograms, but also algorithms that operate faster. And the applications that require speed are growing. For instance, in optogenetics, we need setups that are capable of placing light in the brain exactly at the right time in response to a stimulus. Or in consumer applications, your virtual reality headset needs to adjust in real time to head motion, for instance. Generating holograms fast and with high accuracy is an active research direction in my lab. We recently published a new method to do just that using deep learning. The idea is that we can create a convolutional neural network that will take as input the amplitude that we want to render, A0, and without iterations, directly estimate a suitable complex wave at the image plane. That is a nonlinear operation that CNNs are particularly well suited for. Once we have the complex field, we can propagate it backwards back to the SLM and get the phase modulation that should be applied at the SLM. This whole process does not involve any iterations. The downside, however, is that it needs to be trained. The CNN needs to be trained. To train it, we take the phase output and we simulate the forward propagation of the wave using the laser amplitude AS. And using a loss function, we can now compare the reconstructed amplitude, AR, to the target amplitude, A0, and use the mismatch measurement to update the coefficients of the CNN and improve its ability to compute suitable complex fields. The advantage of this strategy is that we can train our network using application-specific datasets. The only input that we need to train the CNN is a large number of target amplitude that resemble what we're trying to achieve. So we can tailor those datasets to train the CNN to generate, for instance, natural images, or to train for specific dataset that resemble the particular application that we target. The other thing we can do is tailor the loss function to emphasize certain aspects of the reconstruction that we care about. For instance, we may care about efficiency, maximizing the amount of light that is being diverted into the diffracted orders. Or we can maximize for mismatch and penalize any speckle in the rendered images. The loss function can be adapted to any task that we're trying to achieve. So this is perhaps our most exciting results. As you can see, the method that we developed, Deep CGH, is not only orders of magnitude faster than the previous iterative techniques that we discussed, including Gershber-Saxton methods, but also is able to reach, once again, higher accuracy levels, which means that we're able to compute holograms that are better than any other previous method, no matter how long we wait in the optimization process. One of the application areas where having high accuracy holograms is really important is multiphoton holography. In a multiphoton holographic microscope, a femtosecond laser beam generates high pulses of light, high energy pulses, and an SLM will shape this light in order to target simultaneously multiple targets like multiple cells. If we have a low accuracy hologram, the light will be sent towards the sample, but will not contribute to elicit the two-photon absorption process. The result is that the sample will be heated up without providing any relevant signal for our application. So in this experiment, what we've done is we computed a three-dimensional holograms targeting randomly distributed cell size targets, and we computed the very same hologram using three different methods: Gershber-Saxton, a direct optimization method called NovoCGH, and our Deep CGH technique that uses deep learning. We measured under the objective the amount of power that was being received by the sample. So this is a measurement of how much heat is injected into the sample, and we did not observe any significant differences. However, we then placed a slide with a fluorescent layer under the objective, and we captured the fluorescent light slice by slice using a substage camera. This allows us to do a measurement from the fluorescence recording of how much light has been converted into a two-photon excitation process in this fluorescent material. And what we observed is that with the same amount of laser light, we were able to get significantly more two-photon fluorescence using our deep learning model for hologram computation. What that means is that simply by upgrading to a better holographic algorithm, we're able to provide significantly more signal without heating up tissue much more. So this is our experimental recording measurement. So this is a three-dimensional rendering rotating of the same hologram rendered with the three different algorithms. And the fluorescent profile was acquired slide by slide, slice by slice, by scanning the fluorescent slide in depth micron by micron. And we can see in these renderings that we have significantly more fluorescence light available using our deep CGH model. Meanwhile, all these holograms have been obtained with the very same amount of laser power, and therefore all these holograms would contribute equally to heating up the sample. Thanks, everyone. The code for all the simulation we've been discussing, including code for the Novo CGH algorithm and the Deep CGH algorithm, they're all available on our lab website and on our GitHub account. This is the team that has been working in making some of those algorithms possible. And with that, all the contact information is available on my website, and I always happily take questions. Thank you very much.